My pager went off at 02:17 in the morning, that specific jarring sound that every on-call engineer dreads. High error rate on the public API. It wasn't just a blip. It was a sustained, catastrophic failure signal. When I opened the Grafana dashboard on my phone, the request success line had fallen off a cliff, from 99.9% down to almost zero in less than 3 minutes, a complete blackout. Slack was already lit up. The incident channel was a stream of urgent messages and automated alerts. Support was posting screenshots from customers. All requests timing out. Checkout failing. API unreachable. The reports were coming in from everywhere. What made it strange was that our infrastructure dashboard was green, pure deceiving green across the board. CPU steady, memory normal, pod count stable, no node pressure, no obvious spikes in latency inside the cluster. From the outside, production looked like it had disappeared. From the inside, everything looked healthy. That disconnect is what worried me. We were running in AWS across 3 availability zones in US East 1, a massive distributed architecture. The core application was deployed on EKS with around 60 worker nodes using managed node groups, a robust, mature setup. Traffic averaged around 12,000 requests per second during peak hours. Nighttime traffic was lower, around 4,000, but still significant. The public entry point was an AWS application load balancer managed through Kubernetes ingress, the front door to our world. Route 53 handled DNS for our primary domain and several subdomains. We used a mix of public and private hosted zones. Infrastructure was defined in Terraform. CI and CD ran through GitHub Actions with Argo CD handling cluster deployments. Everything was automated. For monitoring, we had the full stack: Prometheus, Grafana, CloudWatch, and Datadog APM for distributed tracing. PagerDuty for alerts. It was a fairly mature setup. Nothing experimental, nothing exotic. This shouldn't have been happening. The first signal was a spike in 5xx responses from the load balancer. The target group health checks were failing, first intermittently, then completely. From the client perspective, DNS resolution was succeeding, but connections were timing out. Users were staring at spinning icons. API clients were seeing connection refused or TLS handshake timeouts. The handshake wouldn't even finish. The connection just died. Inside the cluster, everything was perfect. Pods were running, liveness and readiness probes were green. The database was reachable. Service endpoints were fine. What looked suspicious was that traffic from the load balancer to the cluster suddenly dropped to near zero, even though external request attempts were high. At first glance, it felt like a networking problem between the internet and our cluster. Maybe a security group change. Maybe a network ACL issue. I checked recent Terraform runs. Nothing had applied in the last 6 hours. I opened the AWS console and inspected the target group. Targets were marked unhealthy. Health check errors said connection timed out. I needed to get deeper. I needed to test the nodes directly. I SSH'd into one of the nodes through our Bastion host and manually curled the service endpoint locally. It responded instantly. The application was alive. I then tried curling the service through the internal cluster IP. That worked too. This was definitely an external routing issue. Next, I tested from inside the VPC but outside the cluster, using a small diagnostic EC2 instance. Curling the load balancer DNS name from there hung and eventually failed. That narrowed it down. The issue was not application level. It was somewhere in the path between the load balancer and the nodes. Or was it? While I was digging, our engineering manager joined Slack, then the product lead. We had customers in Europe starting their workday. Revenue impact was real. Every second feels like an hour. Every minute mattered. The pressure was mounting. Someone suggested we had hit a scaling limit, but CloudWatch showed the ALB capacity units were well below thresholds. No throttling. No easy answers. Then one of our platform engineers asked a simple question in Slack. Did anyone change DNS tonight? It was like a light bulb went off in the room. There had been a small planned change. Earlier in the evening, someone from the infrastructure team updated a Route 53 record, described as a minor cleanup. At first, we dismissed it. How could a DNS cleanup break a live production endpoint that was already working? But the timing lined up uncomfortably well. I pulled up the Route 53 console. The A record for api.ourcompany.com was now an alias pointing to a different load balancer than the one we expected. We had 2 load balancers. One was active production. The other was from a previous deployment that had been partially decommissioned weeks earlier. The DNS record was now pointing to the older, unused load balancer. That explained why everything inside the cluster looked fine. Traffic wasn't even reaching us. It was being routed to a load balancer that had no healthy targets registered, a black hole in the middle of our infrastructure. The root cause was a tiny DNS change that unintentionally swapped the alias target of our production API record. A small edit with a massive impact. During cleanup, the engineer recreated what they thought was the correct record. In reality, the Terraform state for that module had drifted. The ARN was outdated. Because both load balancers existed and had valid certificates, the change passed basic validation. There was no immediate error. It looked correct on paper. When the DNS TTL of 60 seconds expired globally, clients started resolving to the wrong load balancer. The outage didn't happen instantly. It propagated. The fix itself was straightforward once we confirmed the diagnosis. We updated the Route 53 record to point back to the correct production load balancer. We had to decide, wait for DNS propagation or attempt a Terraform rollback. Given the urgency, we applied the change directly in the console to minimize delay. We also lowered the TTL temporarily to 30 seconds to speed up recovery for clients that had cached the bad record. We needed everyone back online, fast. Within about 3 minutes, we saw request success rates climbing. Target group health checks on the correct load balancer finally turned green. Error rates dropped steadily. By around 15 minutes after the initial alert, traffic was back to normal levels. The crisis was over. The site was back. We kept monitoring for another hour, watching error budgets and latency percentiles. Everything stabilized. The system was healthy again, but the lessons remained. What actually failed was not DNS itself, but our change management around it. We treated a record update as low risk because it was just a cleanup. Detection was weak because our monitoring focused on application health inside the cluster. We didn't have a synthetic check for the public DNS path. We assumed that Terraform state was authoritative. In reality, it had drifted due to a manual adjustment weeks earlier. The truth was hidden in the state file. Our dashboards showed green because they were looking at cluster internals, not the end-to-end user path. We were blind to the front door. The change didn't go through a formal peer review because it was categorized as minor. That classification was wrong. Every change to production is major. One lesson was that DNS is part of production, not a peripheral detail. A single record can be as critical as any deployment or code change. We implemented continuous validation of critical DNS records. Automated checks now compare Route 53 targets against our expected configuration in real time. We also strengthened our Terraform workflow to detect drift explicitly and block applies when unmanaged changes are found. No more hidden drift. From an observability perspective, we added synthetic probes from multiple regions. They resolve the domain and verify response codes. Every minute, every day. Finally, we reclassified DNS changes as high-impact modifications requiring peer review and a clear, tested rollback plan. No exceptions. A single line in a hosted zone file brought down a multi-region Kubernetes platform. It was a humbling reminder of the fragility of complex systems. In distributed systems, the smallest change at the edge can disconnect everything behind it. Verify everything, assume nothing, and always check the DNS. Because when the success line falls off a cliff, it's not just code, it's the bridge to your users that's broken. Build it back stronger.